Yes, I will send the recording to this class to everyone. I'll put probably an announcement upon Canvas and email it.
Thank you.
You're welcome. Okay, so this is chapter 29, more about our test of significance. So we have Ashley and Chelsea, who are two statistics students, and they're both working on the same problem for their homework. Ashley chooses in advance to use a cutoff significance level of 1%, and Chelsea chooses to use 5%. The question is whether the average cholesterol level among the sedentary females is different from 168 milligrams. And now both cutoff significance levels are valid choices. You're allowed to choose 1%, you're allowed to choose 5%. Now our usual choice is 5% unless you have a reason to choose otherwise, but they're both valid. Now the p-value for this problem is 3.5%. So for number 1, does Ashley reject or fail to reject the null hypothesis? So Ashley had a cutoff of 1%. Now with a cutoff of 1%, 3.5% is actually bigger than that, so that would be a big p-value. And she will fail to reject. Now, does Chelsea reject or fail to reject? Chelsea had a significance level of 5%. So 3.5% is smaller than that. And so she will reject the null. And so for number 3, they both had the same p-value and the same amount of evidence against the null hypothesis. So why did they come to different conclusions? And of course the answer here is just that they had different cutoff levels.
Instructor Lovelace, this is Stephanie from UEN Technical Services. Sorry to interrupt.
Hi, Stephanie.
I understand that you haven't...
Let's go ahead and get back to our class then. Too bad everyone else left. I'm sorry that it took us so long there. So the question is, why did they come to different conclusions?
I can see it slow, but I can't hear you.
But you can't hear me. But everyone else can hear me? Someone can hear me, right? Since you told me you could see, can anyone hear me?
Salt Lake can.
Salt Lake can.
I can hear you over at
Okay.
We're good in Kaysville.
You're good in Kaysville. So this is what we're going to do, because since we've had so many issues, I'm just going to keep going, and if we have just one side that can't hear me, hopefully you'll be able to hear me, since some people can, and if not, you can come watch the movie, I guess, afterwards. So why did they come to different conclusions? So they had different cutoff levels. And the cutoff levels tell you, well, I guess it says it right below, I won't type it again. The cutoff levels of significance, 5% and 1%, tell us how much evidence we require to reject the null hypothesis. So Ashley had a cutoff level of 1%, Chelsea had a cutoff level of 5%. So Ashley said in advance that she would require more evidence to reject the null hypothesis. So there was some evidence, there was enough evidence to satisfy Chelsea's requirements, but not enough evidence to satisfy Ashley's requirements. Okay, so once again, at 3.5%, there was evidence against the null hypothesis, and there was enough evidence to satisfy Chelsea, but not Ashley, because they picked different significance levels. So once again, our cutoff level of significance, 5% and 1%, tells us how much evidence we require to reject the null hypothesis. Now the p-value tells us how much evidence we actually found. So the cutoff level tells you how much you're going to require. The p-value tells you how much you actually find. Now the p-values tell us more than simply whether or not you reject or fail to reject, because they tell you how much evidence you actually found, and that's why it's better to report the p-value than just whether or not you rejected the null hypothesis. Now in our next example, so each of these examples highlight a different aspect of hypothesis testing. So they're all kind of a different topic. So two separate scientists conducted a study to determine if a new diet helped reduce weight. They both chose a cutoff significance level of 5%. So what is the null hypothesis? The null hypothesis always represents the status quo or nothing interesting. The alternative is always what you're kind of hoping to show. So what do you think the null would be in this case? What is the status quo or the not interesting option? That it does not change the weight. So the null is that diet does not change weight. And the alternative would be that the diet helps reduce weight. Now George found a p-value of 5.03%. Should he reject or fail to reject the null hypothesis that the diet does not help reduce weight? Now remember, they are using a cutoff of 5%. So someone go ahead and tell me, with a p-value of 5.03, what are we going to do here?
Fail to reject.
We will fail to reject. So we fail to reject. But Dan found a p-value of 4.98%. So should he reject or fail to reject the null?
He rejects.
He does reject.
So is it possible that they have two different numbers when they're working with, I mean, they came up with two different p-value, but are they working with the same numbers?
Oh no, these guys both have different data sets.
Oh, okay.
Yes, if you have the same data set, you shouldn't get different numbers. Sorry, that's the wrong thing there. They have different sets of data. So yes, definitely different sets of data. And let's see, so George had a p-value of 5.03, so he failed to reject. Dan found the p-value of 4.98, so he rejects the null. So, did they come to different conclusions? Well, yes. Okay. Now remember, a small p-value indicates strong evidence against the null hypothesis. So how does the strength of evidence compare for the two scientists? So remember, the actual p-value tells you how much evidence you have. So the smaller the p-value, the more evidence you have. Well, if their p-values are 5.03% and 4.98%, how do those two p-values compare? Like, how does their strength of their evidence compare? Well,
for George, it seems like the p-value, because it fails to reject, it shows that the diet will not change the weight. But for the other guy, Dan, it seems like the diet will reduce weight.
okay.
So they got conclusions.
So they did get different conclusions. As far as the actual two numbers of 5.03 and 4.98, how do those two numbers themselves compare?
They're not very far away from each other, right?
They aren't. So the two p-values are almost the same. So they both have almost the same amount of evidence. But what happened? So they have almost the same amount of evidence, but one person was just barely above the line and one person was just barely below the line. Now, p-values, they're supposed to tell us more than just whether or not we reject or fail to reject the null hypothesis, because the p-value tells you how much evidence you actually have. And that's why when you write your articles or you summarize your reports, if you have to do a study for school or something, you have to tell people your p-values. They always want to know the p-values and not just your conclusion, because they know that p-values tell you how much evidence you have, and that's a lot more important than just rejecting or failing to reject. And now in actuality, in a perfect world, there's not going to be a sharp border between significant and not significant, between failing to reject and rejecting, just increasingly strong evidence as the p-value decreases. But as humans, we like to make a rule and stick to it. So it's confusing if we try and make too many rules. So if I told you guys, you reject as long as it's under 5%, but oh, well, if you're within like 5.10, go ahead and go for it. That would be too confusing. So we make a rule and we stick to it. So like if you think of driver's licenses, the age for driver's licenses, suppose that Ryan and Levi are friends. Ryan's 15 years and 364 days old, but he can't get a driver's license. Now Levi is 16 years and 1 day old, and he can get a driver's license. So the question is, do you think that 2 days age difference really makes a difference in their driving levels or maturity? No, of course not, right? But we make a rule and we stick to it because it gets too confusing if we try and make exceptions. And if we slid the rule from 5% to 5.03%, the next time why wouldn't we slide it to 5.05%? And then you just keep sliding it and it just gets confusing. So yes, with Dan and George, there's really no difference in the amount of evidence they found. It's the same amount of evidence, almost exactly the same, but one person's above the line, one person's below the line. And so we do get different conclusions. But it's important to remember to look at the actual p-value. So if you were reading this article, you say, oh, 5.03%, yes, he did fail to reject, but I realized there was some evidence that the diet might help, just not enough to say for sure. Or maybe not for sure, because we're never absolutely sure, but there's not enough to make that conclusion. But almost, there is some evidence. Now for our next example, Jillian also conducted a weight loss study for a diet she created. And she wants to know if participants will lose weight on her diet. And she decides to use a cutoff significance level of 5%. So what would be the null and alternative hypotheses in words? So just like previously, the null, the nothing interesting, is that they don't lose weight. And the alternative,
Can you say the participant might lose some weight? Would that be a good null?
say it again.
The participant might lose weight.
For the null? No, the null would still be that they do not lose weight.
It doesn't, okay.
Yeah. And then the alternative would be that the diet helps participants lose weight. Just because, again, the null is your status quo, nothing interesting. The alternative is what you're hoping to show. And so, of course, she's going to be hoping to show that they lose weight on her diet. Otherwise, it's not going, she can't market the diet. Now, she's going to measure the average weight loss of her participants over 6 months. And she found that her sample of people lost an average of 0.3 pounds over the 6 months. And she conducted her hypothesis test and found a p-value of 0.000000031. So that's a very small p-value, right? So lots of evidence that you lose weight. Because it's a very, very small p-value. Lots and lots of statistical evidence. Now at this point I want you to interpret the p-value. So interpretation of the p-value, remember, what does a p-value tell you? So this is a good review of the definition of the p-value. So So the p-value is the probability of getting our sample results or something more extreme if the null hypothesis is true. So our interpretation here would be, so if the null hypothesis is true, so it would be if the diet really doesn't help you lose weight. So if the diet really doesn't help you lose weight, so if the null is true, now it's the chance or the probability of getting our sample result or something more extreme. So there is only a 0.00031% chance of getting our sample average, which was 0.3 or more. So getting a sample average weight loss of 0.3 pounds or more. So once again, it's if the null is true, so if the diet really doesn't help you lose weight, there's only a 0.00031 chance, like change, why is that a change? Chance of getting a sample average weight loss of 0.3 pounds or more. So that's how you actually interpret the p-value, what that p-value actually means. So should she reject or fail to reject the null hypothesis? Obviously that's a very small p-value. And she will reject the null. And how does she interpret her results? She has tons of evidence, because that's an incredibly small p-value. Tons of evidence that her diet helps people lose weight. Now this is kind of a made-up, very extreme example to help illustrate the point. So number 5 asks, are her results statistically significant? So in other words, would she rarely get such a big weight loss by chance, just purely due to chance, if the null is true, so if the diet really doesn't cause weight loss? Big keyword there is if. So that's what statistically significant means. Statistically significant means, well, what's written there. But I also like to think of it as a small p-value, meaning that I have statistical evidence. So statistically significant, the technical definition means, would you get such a big difference just due to chance if the diet really didn't cause weight loss? Okay, obviously in this case, the chance of it happening just due to chance was only 0.00031%. So we don't really believe that it happened just due to chance. And so we have a small p-value, we have statistical evidence. So we have statistical evidence that diet helps you lose weight. And since it's such a small p-value, we have lots and lots of evidence. So we're fairly sure, statistically speaking. But then the question is, does statistically significant mean that it's practically significant? So practically significant means, does it really matter in the real world? So how much did they lose? They lost an average of 0.3 pounds over 6 months. Do you really care if you lose 0.3 pounds over 6 months? I know, I guess some people might. I don't, right? And so I would say no, it's not worth the effort, or not worth the diet, to lose 0.3 pounds over 6 months. So it's not practically significant. So again, statistically significant kind of means that yes, we have statistical evidence. We're kind of sure that this is what happens. Practically significant means, okay, you're sure that it happened. Now does that actually make a difference to anyone in the real world? So just because you have an incredibly small p-value, that doesn't mean that it makes a difference in the real world. Now in our next example, John and Matt have never met or talked. Coincidentally, they both conducted a study to see if the average breaking strength of a new material is less than 40 pounds. Now assume that the population standard deviation is 0.3 pounds. Now John took a sample size of 30 bags and found a sample mean of 39.5. Amazingly enough, so obviously this would also be made up, Matt also found a sample mean of 39.95. However, he used the sample size of 1,000 bags. So these once again would be different data sets that just happen to have the same sample average. So we want to fill out this table. They both used a cutoff significance level of 5%. So for John and Matt, they both have the same sample average. The population standard deviation is 0.3 for each, and they both have a sample size. We want to do, let's say we want to do an actual hypothesis test. So let's go back and look. They want to see if the average breaking strength of the new material is less than 40 pounds. So they are interested in the average. They only have, well, it's two different people doing it, but each person only has one sample. So we have one sample. We're interested in average. So that means it's either a z-test or a t-test. How do you tell the difference between a z-test and a t-test?
If we know the SD.
Yeah, if you know the population SD or the sample SD. So in this case, we know the population standard deviation, so it would have to be a z-test. So this is going to be the z-test for the average. Now before we do a z-test for the average, we should check to see if their sample sizes are big enough. And for the z-test, you both have to have a sample size of at least 30, which they do, so we're good. So let's go ahead and do the work for each of these guys. So for John, we need to find the SE for the average. So it's been a while since we've done this. The SE for your average is standard deviation over square root of your sample size. So his SD was 0.3. His sample size was 30, so 0.3 over the square root of 30. Gives me 0.0547. Now for Z, it's going to be your sample average minus the expected value for the average divided by the standard error for the average. Now his sample average was 39.95. He'd expected, so I guess we should write down the null and alternative real quick. So no, they are. So they want to see if the average is less than 40 pounds. So the alternative would be that the population average is less than 40. So the null would be that your population average equals 40. So our expected average is just equal to your average in your null hypothesis. So in our case, 40 pounds. So expected to get 40 pounds. The standard error was 0.0547. So negative 0.91. Now for the p-value, here's my normal curve. This is a z-test. We'll use the z-table. We're at negative 0.91, and which direction do I want to shade? That always comes from your alternative hypothesis. So the alternative says that the population average is less than 40. So we're going to want to shade to the left. So let's open up our normal table. We're looking for negative 0.91, or this negative 0.9 will do. So the area to the left is 18.41%. So let's come back and fill in our table. So the test statistic for John is z. Z is negative 0.91. The p-value is 18. Just a sec. It's taking away my writing again. So my p-value is 18.41%. So is that a big or small p-value? That would be a big p-value, so we will fail to reject. Now, a big p-value means that you are not statistically significant. Statistically significant, you have to have a small p-value. Okay. So, did John find evidence that the average of all the bags is less than 40 pounds? Well, no. He failed to reject, so he didn't find evidence. So let's now do this for Matt. So the SE for his average, once again, is going to be your SC over square root of, well, I'm not going to write it again. You can just look up at John's. So his SE is going to be 0.3 over the square root of 1,000. So 0.00948. Now your calculator might have told you 9.48 times 10 to the negative 3. So that's the scientific notation. Remember, you just go 1, 2, 3. And fill in your spots. That's how you change it to your decimal. And if you're unsure if you did it correctly, then type in what you think it should be, push enter again, and it'll be back to 9.48 times 10 to the negative 3. So you can double check. And Z, our sample average, he also got a sample average of 39.95. He'd expected a population average of 40, and his standard error was 0.00948. So Z is negative 5.27. So negative 5.27, that's going to be somewhere way out here in the tail, and we're still looking for the area to the left. So if I go to the normal table, negative 5.27, we have to keep going way up. And if I kind of extrapolate here, I'm going to get to basically 0%. Right, so far off the table, those areas were getting smaller and smaller, so we're about to 0%. So this area is about 0%. And in fact, the calculator or my computer when I did it, tells me it's actually 0.00. It's 5 zeros. So that is the actual true p-value if you look it up on a calculator computer to get the exact value. That's a very, very small p-value, right? So Matt's test statistic was negative 5.27. His p-value was essentially 0%. So he will, of course, reject the null because it is statistically significant because it's a small p-value. And so, yes, he found evidence that the average for all the bags is less than 40 pounds. He found lots and lots and lots of evidence that it was less than 40 pounds. Now, this is another good example right here of, okay, Matt has a statistically significant result. He has an incredibly small p-value. He's very, very sure that the population average is less than 40 pounds. However, his estimate of what it actually is that it's only 39.95 pounds. Is it going to make a difference in the real world if he's 0.05 pounds under 40? Or 39.95 versus 40? No. So that's another example of just because it's statistically significant doesn't mean it makes a difference in the real world. It doesn't mean it's practically significant. Oh, I sorry. Have a spot for that down below. So, first of all, why do John and Matt get different p-values? Didn't they all have the exact same thing? What's the only thing that's different?
The sample size.
Okay. The sample size. So they had different sample sizes. And the reason that the different sample sizes matter is that then they have different standard errors for the average, and that means then they have different z-values, which then leads to different p-values, etc., etc., etc. So, just due to the different sample sizes, they got different results, which is important to us. Okay. But continuing on, leading up to that, so do you think there's a practical significant difference between a breaking strength of 39.95 and a breaking strength of 40 pounds? So once again, I would say no, doesn't matter in the real world. I mean, honestly, 0.05 pounds, who cares? So as a note here, Matt's difference of 0.05 pounds is statistically significant because of the large sample size. So specifically because of the large sample size. And so it turns out that very small differences can be statistically significant, meaning you have a small p-value, if you have a large sample size. And specifically, no matter how small a difference might be, if the sample size is big enough, that difference will be statistically significant. And so we've talked a lot about how increasing your sample size is a good thing. So the bigger your sample size, the less likely you are to make an error. And so if you do an experiment like this, you're less likely, if you have a huge sample size, you're less likely to make an error. So you'll be statistically sure that there really is a difference. But the bigger your sample size gets, the more that those small differences that don't make a difference in the real world start showing up as statistically significant. And so it's kind of this toss-up of you want a big sample size, but at the same time you realize if you make your sample size big enough, then your results will be statistically significant just because your sample size is big. So once again, kind of a little balancing act there. So in this next hypothetical example, I'm not sure why I bother writing hypothetical, most of these are. Gideon and Spencer are conducting an experiment on the best time of day to exercise for optimal weight loss. They don't know if it would be better to exercise in the morning or afternoon. They conduct their tests and find that the sample average weight loss is higher in the afternoon. After they look at the data, Gideon and Spencer try to figure out the hypotheses, the p-value, and the conclusion. Now they disagree about the best alternative hypothesis. Now there was something wrong here, so we said after they look at the data, and that's bad, right? So you should choose hypotheses before looking at data. But let's go and look at their two hypotheses that they came up with. So Gideon and Spencer, both of them will have the same null. So the null is that there's no difference in average weight loss for exercising in the morning or the afternoon. Gideon, though, just thinks that there should be a difference for exercising in the morning or afternoon. So he's doing a two-tailed test because he's not saying I think that one is higher or I think that one is lower. So he said going into this experiment that I really don't know whether it'll be afternoon or morning that helps you lose weight better, so I'm going to do a two-tailed test. Spencer, though, for some reason thinks that the average weight loss should be higher if you exercise in the afternoon. So because he thinks he knows which way this relationship should go, it would be a one-tailed test. Now they each found their p-values. Notice that Gideon's is twice as big as Spencer's. The reason why Spencer is only looking at one tail, Gideon is looking at two tails. So once again, Spencer only looked at one tail. Gideon looked at both tails, and both tails will be 3.1%. So when he adds them together, he gets 6.2%. Now, for Gideon, if the p-value is 6.2%, would he reject or fail to reject the null that there is no difference in the morning and afternoon? Well, for 6.2%, that is a big p-value, and he will have to fail to reject. But for Spencer, with a p-value of 3.1%, that would be a small p-value, and he would reject the null. Now, for who was correct, let's go back and look at it again. Hypothetical, Gideon and Spencer are conducting an experiment on the best time of day to exercise for optimal weight loss. They don't know if it will be better to exercise in the morning or afternoon. So ahead of time, they had no suspicion for which way it should go. So which one of these hypotheses should they have chosen based on that? Because they didn't know which one should be better, which of these two sets of hypotheses should they have chosen in advance?
Aren't they both correct?
They both did their work correctly, but they didn't know which way that it should go. So Spencer, he said, well, I think I'll put it as average weight loss is higher in the afternoon. But that was because he messed up and looked at the data first. If you looked at this before you actually looked at your data, and you just say you don't know if it's better to exercise in the morning or afternoon, then you should go with the unspecific alternative of there is a difference. So they don't know if it's higher or lower, so they just say there is a difference and they have to use a two-tailed test. So as far as who is correct, they both did their math correctly. Okay. But you are supposed to pick the hypotheses before you look at the data. Okay. And they didn't know whether afternoon or morning would be higher. They had no suspicions of which one would be higher. So their alternative should have been that there was a difference. They should, because once again they didn't know which one would be higher. So Gideon picked the better alternative hypothesis for the situation.
So I guess I'm confused because if you pick the right one, if you pick the right alternative, however, because he had a bigger p-value to reject, so anyway, he's not correct. It seems like
well, it doesn't mean that he's wrong because he failed to reject. And that actually is a good point. So people realize if I do a one-sided test, my p-value is smaller and I'm more likely to get to reject. And we like to be able to reject because that means then that our experiment was kind of a success, if you will, or our hypothesis was correct, our whole idea going into this was correct. We like to be able to reject the null. And so they realize if I do a one-sided test, I'm more likely to be able to reject because my p-value will be smaller. And so Spencer's kind of falling into this camp of saying, oh, if I just do a one-tailed test, I'll be more likely to reject the null. However, and so you realize that it's nice to do it one-sided, but if you really don't know in advance which one should be higher, ethically speaking, statistically ethically speaking, you should do just a two-sided test. Okay. And you will end up getting a bigger p-value, and maybe that means you failed to reject. But that's kind of just the way we set it up of it's kind of like cheating to look at your data first and then decide which way you want to make the test so that you're more likely to reject it. So once again, you need to choose whether you need a left tail, right tail, or two-tailed test before you look at the data. If the data suggests that a one-tailed test would be more appropriate, so after they looked at the data, Spencer said, oh, we should have done a right-sided test here, then you can do the analysis again, but with a new data sample. Okay, so that's kind of our ethical way to do a study. Okay, so our next example, the average age of all 43 presidents when they entered office is 55.3 years, and the SD is 6.2 years. Explain why it would be inappropriate to conduct a significance test on the hypothesis that the average age of entering presidents is 50 years. So, anyone have any thoughts of why I shouldn't do a hypothesis test in this situation? And I'll key you in. You might want to look at that word.
Okay, I think I'm guessing, but is the SD pretty big? The 6.2 years? It gives a big gap.
The SD is fairly big, so my data is fairly spread out, but that wouldn't actually keep me from doing a hypothesis test.
Is it because you have an average age of the entire population and not just a sample average?
We do. So the 55.3 years is a population average. It's for all the presidents, not a sample average. And it comes down to we don't use hypothesis tests on population data because there is no point. Okay? Because we can say for sure the population average is exactly 55.3 years because we have the data for the population average. So why would you do a test to see what the population average is? We already know it's exactly 55.3 years. There's just no point in doing a hypothesis test. Now in our next example, 3 psychiatrists set out to identify observed characteristics that distinguish schizophrenic patients from non-schizophrenic ones. They considered 77 different characteristics and did 77 two-sample t-tests. So they're doing 77 different hypothesis tests. Two of the tests turned up to be statistically significant. So 2 of those tests had small p-values. Explain why this is not convincing evidence that these 2 characteristics are useful for identifying schizophrenic patients. So what should the investigators do next to decide whether or not these characteristics should be used for this purpose? So this one, you guys probably don't remember, but we said once before that when you do a lot of tests, you expect to see significant results just due to chance occasionally. Okay, so when hypothesis testing, even if the null is true, we expect to reject it just due to chance, having really big chance errors, 5% of the time. If you use a cutoff level of 5%, it's 5% of the time. So even if the null is true, we expect to reject it just due to chance 5% of the time. So for 77 tests, if the null is true, we would expect to make an error and reject the null 5% times 77, which is 3.85 times. So if we're doing 77 tests, even if the null is true and these markers have absolutely no effect, we'd expect to make an error and reject the null about 3.85 times, so about 4 times. So if I now tell you that they rejected the null 2 times, do you think that those markers were really meaning anything, or do you think that maybe those were just the errors that we were naturally expecting? No one wants to be brave there. I don't know why this is not helping me. So I would say if I do 77 tests and I only get 2 small p-values, I'm expecting 4 small p-values just due to chance. So I'm probably not going to get too excited. So we expected 4 small p-values just due to chance. So the 2 small p-values we got probably don't mean anything. But I could collect more data and test again and test those 2 markers again to be sure if I wanted. Like I said, some of these are very technical aspects of hypothesis testing. And our last example is just some true or false questions, and I'm going to go ahead and probably type these so I can get it all the nice little details down, and if you can't write it fast enough, remember I do post these on Canvas. So the first one, a difference that is highly significant cannot possibly be explained by just chance variation. So this would be false. Highly significant just means the p-value is less than 1%. And if the p-value is less than 1%, just means that if the null is true, the difference, or there is a 1 less than 1% chance of the difference happening just due to chance variation. So highly significant means a p-value of less than 1%, which means you have a less than 1% chance of it being explained by chance variation. So a less than 1% chance of it being explained by chance variation. So it's unlikely, but certainly not impossible. I mean, less than 1% chance, that's really not that small of a chance. We have things happen all the time that have a less than 1% chance of happening. Now the next one is that the p-value gives a chance that the null is true. How do you guys feel about that? Is that true or false? The p-value is the chance that the null is true? Okay. Well, I've told you before, the definition of the p-value is complicated, right? Or let's write it down real quick. So the p-value is the chance of getting our sample data, or something more extreme, if the null hypothesis is true. So that's the true definition of the p-value. So how does that compare to me saying the p-value is the chance that the null is true? The true definition of p-value is much more complicated than just saying the chance that the null is true, correct? And so I've told you, if I try and give you a definition of the p-value and it looks simple, you know it's going to be wrong. Right? Because the true definition is very long and complicated, and you cannot simplify it no matter how much you try. So the p-value is the chance that the null is true, that would be false. And number 3, if the p-value is greater than 5%, we do not reject the null hypothesis. So someone go ahead and tell me what you think about this one.
It's false because it depends on where your cutoff is.
Oh. Okay. So you're saying it depends on a cutoff. If I tell you use a cutoff of 5%, then what would you think?
I didn't read that right, sorry.
Well, technically you're correct. If I didn't tell you the cutoff, then you couldn't truly answer it. But if I tell you the cutoff of 5%, then is this one true or false?
We would fail to reject.
True. So it is a big p-value, bigger than 5%. So, true. This next one might seem slightly confusing, or you might look at it and wonder, oh, would I have thought this, but I have seen on the other professors' exams. So in a z-test, if the test statistic is 0.02, we reject the null hypothesis. Now the confusing thing here is, did they tell us which tail? They didn't tell us which tail. So we would have to consider all 3 situations. So here's our 0.02. We might have to shade to the right. And if we have 0.02, I might have to shade to the left. Or I might have to shade both tails. So it might be to the right of 0.02 or to the left of 0.02, or maybe both tails, because it didn't tell us. But let's go ahead and see if we can figure out what these p-values would be, and maybe they all give us the same conclusion and we can answer this question. So if I go to my normal table and look at 0.02, so z is 0.02, well, the closest area is about this 0.00, so about 50%. So that means the area here to the right, or to the left, would be about 50%. And the area to the right then, if we use the complement rule and subtract 100%, would be, once again, about 50%. And if we do both tails, then each tail is about 50%. So my total p-value would be 100% if I add it together. So no matter which tail actually, just a sec on this one, I want to make a note so you guys remember it later. Total p-value is 100% for the option with both tails. So no matter which tail, we have a big p-value. So we should fail to reject. So they said in a z-test, if the test statistic is 0.02, we reject. So this one would be false. Now I think the part that she was assuming people wouldn't realize is when it said the test statistic is 0.02, the test statistic means that z equals 0.02. And she figured people might read that and say, oh, p-value is 0.02 and reject the null. So you have to pay attention. The test statistic is z, and then that makes your p-value close to 50% or 100%, and so you have to fail to reject the null. And for number 5, our last one, for a t-test, it doesn't matter whether the individual data values follow the normal curve. So let's answer this one, or say what we know first. So what we know is for a t-test, you need a large sample size, basically at least 30. Or normal data. And this normal data is the individual values. So when it says for a t-test, it doesn't matter whether the individual data values follow the normal curve, would that be true or false? It's false because they have to follow a normal curve or have a large sample size, but if you have a small sample size, then yes, they have to follow the normal curve for you to do the test, so it does matter.